Lesson 3.11, Local Linearity. This lesson is about taking the tangent line and using the tangent line to approximate values on a particular function. So say I wanted to find the height of the function here. It's a little bit past a. All right, if you plug that into the original function, it's not a nice number. So what this section is all about is saying, well, look for a nearby number that is easy to evaluate in your function. Then you can create the equation of the tangent line, and the tangent line models the height of the curve at any given point near this desired point. So say I wanted to find the height here. My tangent line approximation is an underestimate, but it's pretty close to what it is. Same thing on this side. If I wanted to find the height here, I could use the tangent line to approximate its height, but again, it's a little bit lower. The other thing we have to talk about is the approximations that we're getting from this tangent line. Are they going to be underestimates or overestimates? In both of these cases, we use the tangent line, and it would be underestimates because the tangent line falls below the curve. What happens is the concavity of a curve determines whether these approximations are going to be under or over. In section 4.3 in the book, as a model or a reference, that's where they talk about concavity, but we kind of need to use it a little bit here for the tangent lines. Concave up basically means that your function is kind of a bowl shape, or think of it as a valley shape, or it's a part of the valley or part of a bowl for concave up. Concave down, I like to think of as a mountaintop or a piece of a mountain. So all these examples you can see, you have concave up versus concave down, valley versus mountain. So I will be referring to the concavity as concave up or concave down as we go through this section. The formula for a linearization is simply the formula for finding the equation of the tangent line. We need slope times x minus a. A is the desired point on the function that is easy to find values at, plus the y value. The order in which you put these does not matter. You can use either format for a linearization. How does it work? Let's take the example of the square root function given here. We're going to find a local linear approximation at 4, so the tangent line at 4, which I've got modeled for you, and then we're going to use it to approximate a value a little bit right of 4. Well, it's kind of hard to see because they look mushed together here, but this tangent line is above the curve after 4 and before 4. The reason it's above is because this is considered to be concave down. It's like part of a mountain. How do we get the approximation? I need a point and I need a slope, and I'm going to use my point and slope at 4 because those are easy to work with in the square root function. So f at 4 is equal to 2. F prime at x is what I'm going to find first in order to find the slope at 4. F prime of x is 1 over 2 square roots of x. That's coming from 1/2 x to the negative 1/2. F's derivative at 4 is going to be 1/4. Again, noticing the labeling of the answers and the work. Please try to work on your labeling of pieces. To find the approximation, I'm going to now create my linearization. So L of x, the linearization, is equal to the y value plus the slope times x minus a. To find the approximation, that's a linearization, so you can do L of 4.2, or you could say f at 4.2 is approximately equal to 2 plus 1/4 times, oops, and I forgot, this a value shouldn't be an a value, it should be a 4. And then I'm going to put 4.2 minus 4. Well, what does that become? That becomes 2 plus a quarter. These are usually done non-calculator. This is 2/10, which is 1/5. So I end up with a linearization amount at 4 of 2 and 1/20. Well, if I look at 4, and to the right of 4, it's slightly above the 2. So this answer is making sense. Then the approximation, I'm going to say L at 4.2 is an overestimate because the function f of x is concave down on 0 to infinity. So because my curve is concave down, that means the tangent line is above, so we have an overestimate for our approximation. Number 2, use linear approximation to find this value at 0.1. So 0.1 is kind of a crazy number to put into that function. So the linearization process is going to give me an approximation to that value, and we'll tackle that in a moment. First, I'm going to find f at a nice point to plug in. Well, what is 0.1 really, really close to that is easy to plug into that function? I'm using 0. Hopefully everybody else was thinking 0. So f at 0 gives me 4. So this is the desired point that I am working with. And then I'm going to say f prime of x. I'm going to find the derivative first, which is 2x minus 3. Then I'm going to find the slope at 0, which is negative 3. Well, if I'm looking at this quadratic, x squared means it opens up. It's got a y-intercept of negative 4. And the vertex is found at 1.5 with something. All right, so since it's opening up, 1.5 with something would be like probably down here. So I'm just going to do a quick little visual here. And so then at 0.1, we're still really close to that 0 point, and we notice it's heading down. So it makes sense that we have a slope of negative 3. If I draw the tangent line here to model it, try to draw the tangent line here at 0, 1. I should use my ruler. The curve is above the tangent line on both sides, so that means this approximation, even though it's really mushy here, should be an underestimate because the curve is higher up than the tangent line. To find that approximation, I'm going to say f of 0.1. You can use L of 0.1. But because I'm using f, I'm now going to say this is approximately equal to the y value, which is 4, minus the slope times the x value, which is 0.1, minus the input value, which we chose, which is 0. So we end up with an approximation of 4.0. Let me take that back. 4 minus 0.3. So we end up with an approximate height of 3.7. Looking at this now, this linear approximation, what is it in relation to the curve? Well, f at 0.1 is an underestimate because f of x, our original function, is concave up on its entire domain. But if you had it changing concavity in between, say you had a cubic or a fourth degree, then this interval would change. It wouldn't be everywhere. It would kind of, you would pick a section that is around that group to model the behavior. Find the local linearization at 1. So to find the linearization at 1, then I'm going to start with finding f at 1. F at 1 is equal to 1. The next thing I need is the slope, so I'm going to say f prime of x, and that would be negative 1x to the negative 2, or negative 1 over x squared. F's slope at 1 is equal to a negative 1. So my linearization in general is L of x equals, and I'm going to flip it around and do it the other way. I'm going to say start with a slope of negative 1 times the quantity x minus 1 plus my y value of 1. I'm going to use this approximation to estimate f of 1.1. So I have negative 1.1 minus 1 plus the 1. So what does that give me? That gives me 1 minus 0.1, which gives me 0.9. Is the estimate too high or too low? Well, in order to determine that, I have to recall the graph of 1 over x. 1 over x looks like this and this. Oops, not over far enough. We care about this particular section, and this particular section is concave up. If it's concave up, then if I picture drawing a tangent line at 1, look at how the tangent line is falling below the curve. So f at 1.1 is too low of an estimate, because f of x is concave up on, and I'm just talking about this section of the graph, so I'm just going to say from 0 to infinity, because that includes the 1. Use a linear approximation to estimate the tangent of 0.8. For this one, I have to think what value is going to be good to plug into the tangent function. That's going to be close to 0.8. Well, I have to work with radians. Radians have pi's in them. So if I take pi over 2, pi over 2, pi over 4, pi over 3, pi over 6, like any of those, which one would be the best to get to 0.8? Well, remembering that pi is a tiny bit over 3. So I'm going to think pi is like 3, and then I'm going to say 3 divided by who gets me the best approximation for 0.8. I'm going to say let the a value be pi divided by 4. 3/4 is 0.75. It's a little bit above that because it's a little bit above 3. So I'm going to now use f at pi over 4 to find the nice y value to use. That should be tangent of pi over 4, which is a 1, because I'm saying f of x is equal to tangent of x. F prime of x is equal to secant squared of x. At pi over 4, I'm dealing with a 45, 45, 90. Flipping the cosine. Cosine is 1 over root 2. If I flip it, I get a root 2 and square it. So that means the slope value should be a 2. The linearization in general is going to be 1 for the y value plus 2 times x minus pi over 4. Then the linearization at 0.8 would be 1 plus 2 times 0.8 minus pi over 4. And I'm going to leave this one in this form because these are usually non-calculator, and I'm not going to do 8/10 minus pi over 4. I'm not going to go through all that arithmetic if I don't need to. The only time you would need to is if you were looking to match up an answer to a multiple choice question. The last problem here, the only information we have about a function f is that we have a point on function f, 0, -2, And the graph of the derivative is shown below. So this graph, I'm going to label it f prime of x. This represents the slope values. Local linear approximation at x equaling 0. So what do I need to know? I need to know f at 0. That's given at -2. And then I would need to know f prime at 0. Well, this is the f prime graph. At 0, it looks like it's at 9. So the linear approximation at x equals 0, I would use this linearization to find it. -2 plus 9 times, technically x minus 0. You can write x minus 0 or just write x. Either one is okay. So that's the local linear approximation at 0. Now we're going to use that linear approximation to find the slope at -0.1. So I'm going to say f prime at -0.1 is equal to -2 plus 9 times -0.1. That one's not too bad to do. To simplify out, we get -2.9. Now the question is the approximation in part B an over or an underestimate? Well, this one we would have to wait because we don't know information about f of x and we don't know the concavity, so let's not add that in right now.